So just a little advertising for Union College. Those of you who don't know, we're a small undergrad-only institution in upstate New York, about 2,000 students. And so here's a nice shot of campus at the fall. It's a nice time, not so much in the winter, but in the fall, it's a very nice time. Okay, so photoacoustic microscopy. Most of us probably know that blood is a very strong optical absorber. So if you want to image something besides blood, you need to go at longer wavelengths, as mentioned in some of the previous talks. And so you can also use some contrast agents like ICG or gold nanorods. But as far as, how do you get light at that wavelength? So as far as conventional methods, right, dye lasers, OPOs, they tend to be big, bulky, expensive, and fairly low rep rates. So for microscopy, right, we're going for higher rep rates, and the pulse energy is not as critical. So the approach that we're taking is to start with a compact high rep rate pulse laser and use nonlinear fiber optics to create new wavelengths. And then you can use a tunable filter to pick whatever wavelength you want. So as far as this wavelength generation mechanism, one way to do it is to use a stimulated Raman scattering. So this describes when a laser pulse interacts with the vibrational modes of the material, like in the glass molecules in a fiber. And so that produces a series of frequency downshifted lines. And so what happens, as an example, is that if you send 532 nanometer pulses through, let's say 50 meters of single mode fiber, is that you can produce, in this case, a dozen extra wavelengths. And so that works well, but the question we were thinking of was, could you use, let's say, a multi-mode fiber to produce new colors for photoacoustic microscopy? And one advantage is that they tend to be cheaper than, let's say, the polarization maintaining fiber used for this example. But perhaps more important is that the larger cores may lead to higher power handling, so you can potentially scale to higher energies. So just a quick review of fiber modes. So single mode fiber, your core is typically like 5 microns in diameter. And so the single mode that you get, one way of the notation is this LP, linear polarization mode, LP01, right? So the 0 is the azimuthal, right, along the angle, and then the 1 is for radial. And so the actual intensity distribution is very Gaussian-like. Now, if you make the core a little bit bigger, let's say on the order of 8 to 9 microns, then you can fit a few higher order modes, right? And so in this case, you would, let's say, have 4 LP modes. And so the actual intensity distribution has a more of a lobed structure, right? So the question is, all right, if we have some modes here, how do they produce new wavelengths? And so it turns out that FourWave mixing actually is quite prominent in this situation. So one form common in fibers is degenerate FourWave mixing. So that describes a case where you have two input waves that are the same frequency or the same wavelength and same K vectors. And so they interact and produce 2 more waves of different frequencies. Typically, they're called the signal and the idler. Now, in order for this to be efficient, though, is you need phase matching. So this is a parametric process. So basically, your wave needs to travel at the same speed down the fiber. Unfortunately, if you start with 532 nanometer light, glass has a very strong dependence for the refractive index on wavelength. And so you're not going to get phase matching by itself. However, if you actually have your 2 532 nanometer photons propagating in different modes, it turns out that it is possible for the dispersion between different modes to cancel the effect of the dispersion in the refractive index. So the overall effect is you actually do get phase matching, and that's quite a happy case. So we're basically leveraging that, and so then you can actually develop your sidebands, and they can grow in intensity and actually create more sidebands. And eventually, you can actually get a continuum, all right? So for our experimental setup, we start with a Q-switch laser. Rep rate's 20 kilohertz, pulse energy is about 15 microjoules, and duration is about 1.5 nanosecond. We send it through about 100 meters of SMF-28 fiber, so this is pretty much the industry standard for telecom applications. It's single mode at 1550 nanometers, but again, we're operating at 532, so that smaller wavelength means you get a few modes in the fiber. And so through FourWave mixing, you create a whole bunch of new colors, and so then we could, or we do, send it through an optical filter to get whatever wavelength band that we want. So if you measure the spectrum coming straight out of the fiber, it looks something like this. So you have your initial 532 here, you got a few discrete lines due to stimulated Raman scattering, and then you get this broad continuum due to FourWave mixing. So it's peaked at about 725 nanometers. In terms of energy, if we picked a filter that let through anything greater than 750 nanometers, you get about 1.3 microjoules of energy. And so the extent of the spectrum does depend on the strength of your input, as you can imagine. And so if you vary the input energy, so shown on the bottom here is the maximum case. And so then as you work your way up through this plot, obviously if you have smaller and smaller input energies, right, then you're going to generate fewer wavelengths, right? So this characteristic slope is what you would expect from something like from a nonlinear optical process. Okay, so as far as the spatial modes coming out of the fiber, at the shorter wavelengths, you get some structure, right? You kind of have a donut shape that's characteristic of a higher order mode for shorter wavelengths. But then at the intermediate wavelengths, you actually get some better behaved looking mode shapes. And what was somewhat surprising is that at the very long wavelengths, around 800 nanometers, you get very well behaved modes that look almost Gaussian-like. So indeed, if you were to try to fit a Gaussian to, let's say, the 800 nanometer profile, it fits quite good. Of course, what really matters, though, is image quality, right? Spatial resolution. So if we actually image a USAF target, so we chose 3 different wavelength bands and then do the usual like edge spread function and the derivative to get the line spread. So as far as the full width half max of that's how we define our resolution. And so we end up with these 3 cases. So at the shorter wavelengths, that I will not try to point out with the laser pointer, the resolution is clearly not as good. It's about 13 microns horizontally, 12.5 vertically. So again, that's actually not that surprising that it's worse because as we saw before, the actual spatial modes were a bit more complicated at the shorter wavelengths. Meanwhile, for the longer wavelengths where you have a Gaussian-like beam is that you can focus much tighter and get better resolution. Either way, though, the resolution is quite good. So as far as an actual photoacoustic experiment, this is the usual optical resolution photoacoustic microscopy system. So we got some scanning mirrors and we focus the beam into the sample. Well, in this case, we just have dye-filled tubes, right, 250 micron inner diameter. And then we have a 25 megahertz transducer for detection and an amplifier. And so again, as you scan the laser, right, you acquire your signals. So if we use all the wavelengths, right, then we can see both tubes. So the left one is IR820 dye at 200 micromolar, and the right side, the right tube, is a red dye. And then if we use a long pass filter, then as you would expect, we indeed only see the left tube where the IR820 is filled. And then if we just use a short pass filter, then we see the red ink tube. So basically that's just to demonstrate, right, the ability to pick the different wavelength bands. So as far as trying to scale to higher energies, right, larger cores possible. So as far as, you know, maybe the higher number of modes in the larger core fiber can lead to increased FourWave mixing. But when we actually tried that experiment, it turned out with the larger core fiber that we did get a continuum, but it didn't extend very far in wavelength, so about 650 nanometers. So therefore, in the end, probably what's happening is that if you have too many modes, then you have just too many channels, and so therefore your energy tends to get diluted in one sense. So you can't get high enough wavelengths through this process. Right, we had shown that as far as using a multi-mode fiber, just a few modes that, yes, we can actually create a good range of wavelengths for photoacoustic microscopy, but as always, we're trying to scale to higher energies. And one way we're going to do it is to actually explore polarization control, because we found that if you use polarization maintaining fiber, that has a huge impact on the range of wavelengths you can produce. And so that's basically what we're going to try to investigate. And I would acknowledge my funding source.